Hey, lads and ladies, welcome back to Calc 2. First things first, I want to apologize for not having finished grading your tests yet. I am working on them as we speak, but had some issues come up with the testing center and some issues come up with one of my other my pre-calculus class. A lot of cheating there that I've been having to deal with through Rodkin's office. But I am working on them right now. I've got the first few online tests graded, and we'll continue grinding those out today. I do apologize for the time it's taking, but it's just the nature of the beast here. We've got so much online testing and so many versions of each test. Today is going to be a fun day for us because we're going to start talking about Taylor's theorem in earnest, which is a really cool topic that we introduced at the end of class last time. And I don't want to scare you too much with the proof or derivation of Taylor's formula. We kind of went through the first few steps of a special case of it last time. Today, though, I am going to show you where Taylor's formula comes from, and we're going to get some practice using it. So that is that. I'll say so far the tests I've graded are actually looking pretty good. There are, of course, plenty of errors, and that's the nature of the beast. This is a hard test, but I'm generally impressed so far. Kudos. This is MAC2312, section number 004, which is Calc 2. And today is the 15th of November, 2021. Today, we're going to cover the last section that we're doing on power series. I'm talking about Taylor's theorem, which is section 1110. And we did introduce this last time a little bit. I think the kind of least scary way to do this is to show you the formula and then show you where the formula comes from, and try to do that all quite quickly, and then get lots and lots of practice with that formula. So I'm not going to waste any time here. I'm just going to show you what the thing is. The textbook talks about a separate theorem for estimation from Taylor's theorem. I'm not concerned about that. I'm just concerned about showing you the recipe. We already have an estimation theorem from section 11.5, the estimation theorem for alternating series, and that's the only estimation theorem that I'm going to require you to learn. Okay. So Taylor's theorem says if f, say f of x, is infinitely differentiable at x equals a, which means like f primed of a exists, f double primed of a exists, f triple primed of a exists. So, i.e. f primed of a, f double primed of a, and so on, all exist. Then f can be written as a power series. So f of x is equal to sigma n from 0 to infinity Cn centered at a. Cn times x minus a to the n. So this gives us a condition under which we know a function can be written as a power series. It has to be infinitely differentiable at the center. So if you have a function which has derivatives of all possible orders at some number, then that function can be written as a power series. That on its own is an incredibly powerful statement. So there's a sort of big question so far. We haven't poked at it at all, but what functions can be written as power series? Can you write any function as a power series? The answer turns out to be no. power series are big, long polynomials, and those are always smooth functions. They're nice. Their graphs don't have any jumps or asymptotes or anything like that. And the same conditions are necessary to get any function as a power series. It has to be a nice, smooth function, meaning derivatives of all possible orders exist. Function is continuous, differentiable, twice differentiable, 3 times differentiable, and so on. So if you have an infinitely differentiable function, then you can write it as a power series. And the coefficients of the power series are given in terms of the derivatives f primed of a, f double primed of a. After the second derivative, we usually start writing superscripts like this. So f superscript 3 of a. The fourth derivative at a would be f4 of a, and so on. In general, the nth derivative of f evaluated at a is this guy. By the formula, Cn is equal to the nth derivative of f evaluated at a divided by n factorial. All right, that's it. That is Taylor's theorem. So any infinitely differentiable function can be written as a power series centered at a, where the coefficients are the nth derivative of that function evaluated at a divided by n factorial. And I started to prove a special case of this where the center is 0 for you at the end of class last time. I want to run through that argument just a little bit here. If f of x is sigma n from 0 to infinity, Cn times x minus a to the n, that is C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed plus C4 times x minus a to the 4 plus and so on. So f of a, if you plug the center into this series, you just get C0. Right? Because this would be a minus a, this would be a minus a squared, this would be a minus a cubed. All of these terms become 0 when you plug in a for x. So f of a is equal to C0 plus, all of these are 0, just C0. Differentiating that series above, the constant term C0 goes away and you get C1 plus the derivative here is 2C2 times x minus a plus the derivative here is 3C3 times x minus a squared. The derivative of this is 4C4 times x minus a cubed. The next term here would be 5C5 times x minus a to the 4, and so on. And if you plug in a here for x, on the left-hand side, you get f primed of a. And over here, this would be 0, a minus a. This would be 0, a minus a squared. This would be 0, a minus a cubed. So f primed of a is C1. And this is how we cook up this formula in general. You just keep differentiating and then plugging in the center. If I differentiate again, f double primed of x, now C1 goes away, and this piece becomes just 2C2 times this derivative is 1. Plus, this piece becomes 3 times 2 times C3 times x minus a. Plus, this piece becomes 4 times 3 times C4 times x minus a squared. Plus, differentiating this piece, I get 5 times 4 times C5 times x minus a cubed. Plus, the next term here would be 6 times C6 times x minus a to the 5. So his derivative would be 6 times 5 times C6 times x minus a to the 4, and so on. And now when you plug in the center, a, on the left-hand side, you have f double primed of a. On the right-hand side, this term, this term, this term, this term are all 0. You just get 2 times C2. We're going to do 2 more of these. And then we look to the pattern. f3 of x, the third derivative. The derivative of 2C2, that's a constant, that's going to be 0. The derivative of 3 times 2 times C3 times x minus a is 3 times 2 times C3. The derivative of x minus a is just 1. The derivative of 4 times 3 times C4 times x minus a squared is 4 times 3 times 2 times C4 times x minus a. The derivative of 5 times 4 times C5 times x minus a cubed is 5 times 4 times 3 times C4 times x minus a, I'm sorry, C5, x minus a squared. The derivative of 6 times 5 times C6 times x minus a to the 4 is 6 times 5 times 4 C6 x times x minus a cubed. And so on. So plugging in a, we see that the third derivative of f evaluated at the center is going to be 3 times 2 times C3. And I'm leaving that as 3 times 2 rather than writing it as 6, because remember what we're after here. We're trying to prove a formula that involves factorials. I claim that Cn should be the nth derivative evaluated of a divided by n factorial. So I'm going to help us see that this is a factorial by leaving them as products. All right, we'll do one more. If I differentiate one more time to get f4 of x, 3 times 2 times C3 is a constant. It will differentiate to 0. 4 times 3 times 2 times C4 times x minus a differentiates to 4 times 3 times 2 times C4. Plus 5 times 4 times 3 times C5 times x minus a squared differentiates to 5 times 4 times 3 times 2 times C5 times x minus a to the 1. Plus 6 times 5 times 4 times C6 times x minus a cubed differentiates to 6 times 5 times 4 times 3 C6 x minus a squared. And you see the factorials showing up, right? 4 times 3 times 2, 5 times 4 times 3 times 2, 6 times 5 times 4 times 3, and when I took another derivative, this 2 would come down. You plug a in here, you get f4 of a is 4 times 3 times 2 times So what do we have? Well, solve this for C4, and you get C4 is F4 of A divided by 4 times 3 times 2, which is F4 of A divided by 4 factorial. Solving this for C3, we get C3 is F3 of A divided by 3 times 2, which is F3 of A over 3 factorial. And more, same here, right? C2 is F double prime of A over 2, and 2 is the same as 2 factorial. Here, C1 is F prime of A over 1, and 1 is the same as 1 factorial. And here C0 is F of A over 1, which is F of A over 1. So the pattern in blue is pretty clear. C0, oh, sorry, 1 is 0 factorial. C0 is the 0th derivative. We differentiate 0 times, plug in A, divide by 0 factorial. C1 is the first derivative evaluated at A divided by 1 factorial. C2 is the second derivative of F evaluated at A divided by 2 factorial. C3 is the third derivative at A divided by 3 factorial. C4 is the fourth derivative at A divided by 4 factorial. And in general, Cn would indeed be the nth derivative of F evaluated at A divided by n factorial as claimed. So this was pretty hot shit when it was discovered. And the connection between being infinitely differentiable and having a power series is a big, big deal in big boy analysis. And for us, what this is a formula. For us, this is a formula that tells us how to get a power series for a function if you can't use the geometric series trick or integration and differentiation of a geometric series. So there are lots of functions where neither their derivative nor their antiderivative is a rational function. Kind of the take-home lesson from section 11.9 is if your function is a rational function, or its derivative is a rational function, or its antiderivative is a rational function, then you can write that rational function as a power series using the geometric series trick, and then differentiate or integrate to get the original function as the derivative or antiderivative of that power series. But for example, e to the x, his derivative is always just e to the x. His integrals are always just e to the x. So there's no way I could ever write any derivative of e to the x as 1 over 1 minus something. That geometric series trick will never work for e to the x. Taylor's theorem, on the other hand, works really well. Same is true for like sine x, cosine x, and a few other quite famous functions that we'll take a look at here. But the major result in section 11.10 is power series for the exponential sine and cosine. And those are the ones that I'm going to require you to remember. So here's our first big example. I'm going to find a power series for e to the x. I've already shown you this power series, I think at least once, and told you what it is, but we haven't verified it. And this is a good first example for using Taylor's theorem because it's so simple, because the derivatives of e to the x are always just e to the x. How do we do this? Well, anytime you want to use Taylor's theorem to cook up a power series, I recommend making the following table. N, Fn of x, Fn of your center, which here is 0, and Cn. Give yourself plenty of space with the middle columns, because you're going to be repeatedly differentiating. Now here, this is going to be very simple, but in general, this column tends to be the messy one. If n is 0, if we differentiate 0 times, e to the x is e to the x. And then plugging in the center, you get e to the 0. And then Cn, remember, is Fn of 0, or Fn of a in general, divided by n factorial. So this e to the 0, which is 1. So this would be 1 over 0 factorial. And I'll leave it like that. When n is 1, the first derivative of e to the x is e to the x. When you plug in 0, you still have e to the 0, which is 1. And dividing by 1 factorial, you get 1 over 1 factorial. You can smell where this is going already, I bet. When n is 2, we differentiate twice. E to the x is still e to the x. And plugging in 0, we still have e to the 0, which is 1. And dividing by 2 factorial, I get 1 over 2 factorial. The pattern here is achingly simple. In general, the nth derivative of e to the x is e to the x. Plugging in 0, you will always get 1. So Cn is 1 over n factorial. Your tables for Taylor's theorem will always look something like this. N on the left, the nth derivative next, the nth derivative evaluated at the center next, and then the previous item divided by n factorial on the right. And what we discover from our bottom thing here, that Cn is 1 over n factorial, which means f of x is sigma n from 0 to infinity 1 over n factorial times x minus 0 to the n, i.e., that is e to the x is sigma n from 0 to infinity. X minus 0 to the n is x to the n times 1 over n factorial is divided by n factorial. This is the power series for e to the x. And in previous problems, we have shown that the interval of convergence here is negative infinity to infinity. This is one of our early ratio test examples. I'm not going to run back through that. So just like the 1 over 1 minus u, inverse tangent of u, natural log of 1 plus u, those power series that you need to remember, this is one that you need to remember. Questions on what we did here with the table? let's see. Normally I would do sine next. Yeah, if I could list it. Let's find a power series for f of x equals sine x, centered at a equals 0, and do it using Taylor's theorem. Like e to the x, we really don't have a hope of writing this as 1 over 1 minus u. It just can't be done. Sine x is not a rational function, neither are any of its derivatives. But Taylor's theorem gives me a path. And again, the derivatives are nice here. I'll make my table. This third column is always Fn of the center, and I'm working with the center 0. The pattern here is pretty nice, but it's not quite as obvious. So if n is 0, I differentiate 0 times. I just have sine of x. Plugging in 0 for x is sine of 0, which is 0. So C0 would be 0 over 0 factorial, and that's 0. Differentiating once, the derivative of sine x is cos x. Plugging in 0, cos of 0 is 1. So C1 would be 1 over 1 factorial, which I'll leave as that. Differentiating twice, the derivative of cos x is negative sine of x. And evaluating at 0, negative sine of 0 is 0. So C2 would be 0 over 2 factorial, which is 0. The only reason I'm simplifying the 0 guys is to emphasize that a lot of these coefficients are going to be 0. The others will all fall into a nice pattern. When n is 3, I'm looking at the third derivative of sine, which is the derivative of negative sine, which is negative cos x. Plugging in 0, negative cos of 0 is negative 1. So C3 would be negative 1 over 3 factorial. Differentiating a fourth time, the derivative of negative cos x is negative sine x, or just sine x, which when evaluated at 0 gives 0. So C4 would be 0 over 4 factorial, which is 0. I'll do 2 more maybe. When n is 5, the derivative of sine x is cos x. Evaluated at 0 is 1. So C5 would be 1 over 5 factorial. Maybe to help you see the pattern, we'll do 2 more. When n is 6, the derivative of cos x is negative sine x, which when evaluated at 0 gives 0. So this would be 0 over 6 factorial, which is 0. And when n is 7, the derivative of negative sine, the seventh derivative of sine, is negative cos x, which evaluated at 0 is -1. So C7 would be -1 over 7 factorial. So what do you notice about these guys? When n is 0, 2, 4, or 6, Cn is equal to 0. Cn is equal to 0 for all the even integers. And otherwise, you get 1 over 1 factorial, -1 over 3 factorial, +1 over 5 factorial, -1 over 7 factorial. Actually finding a clean formula for the Cn's here is a little bit hard because you have to consider the even and odd cases separately. I think the simplest way to take this table and discover the power series for sine is to just write out what the table tells us. This tells us that sine x, f of x, that would be C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 plus C5x to the 5 plus C6x to the 6 plus C7x to the 7 plus C8x to the 8 plus C9x to the 9, and so on, is, well, C0 was 0. C1 was 1 over 1 factorial, so that's 1 over 1 factorial times x. C2 was 0, plus C3 was -1 over 3 factorial. So I have that times x cubed. Plus C4 was 0, so this whole term is 0. Plus C5 was 1 over 5 factorial, so I have that times x to the 5. Plus C6 was 0, so this whole term is 0. Plus C7 was -1 over 7 factorial, so I have that times x to the 7. C8, following this pattern, would be 0. What is C9? If we follow this pattern, what would the coefficient of x to the 9 be?
1 over 9 factorial.
Very good. This is 1 over 9 factorial times x to the 9. All right, now let's write this without the zeros. I get 1 over 1 factorial times x minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the 5 minus 1 over 7 factorial times x to the 7 plus 1 over 9 factorial x to the 9, and so on. The next term would be -1 over 11 factorial x to the 11. So this is the first few terms of the power series for sine. And I would like to write this in sigma notation. What pieces live inside the sum? Well, I've got +1, -1, +1, -1, +1. So there's something like a -1 to the n going on upstairs. This is an alternating series. The powers of x are 1, 3, 5, 7, 9. That's x to the 2n plus 1. And the factorials downstairs match the powers of x. So this is 2n plus 1 factorial. And we're summing from 0 to infinity. This is the power series for sine x. And like the power series for e to the x, you need to remember this forever and ever on. The IOC here is also -infinity to infinity, and it's a quick ratio test to get it. Like I said, finding a formula for the Cn is a little tricky. The reason we wrote this out and kind of collapsed it down like this is because all the even terms are 0. And once you get rid of all those even terms, you can write this as x to the 2n plus 1 instead of x to the n. So the kind of thing to remember is if you write out a bunch of these CNs in your table and you don't see the pattern right away, or you find it hard to write down a formula for Cn in general, go ahead and write out the first few terms of the series that come from these guys. Simplify, and then see if you can collapse that thing into sigma notation. Sometimes that will make life easier, like it did here. If you really want a formula for Cn in general, it's a bit odd, pardon the pun. You have to break it into cases. It's 0 if n equals 2k is even. And it's -1 to the k over 2k plus 1 factorial if n equals 2k plus 1 is odd. Now, I wouldn't expect you to come up with this, but I would expect you to be able to write out the first few terms of the series from this table, and I would expect you to be able to go from here to here. Questions on what we did with this? Okay, we have our power series for e to the x now. We have our power series for sine of x now. I want a power series for cos x next. And I'm going to ask you, what do you think is a good way to get a power series for cos x? Centered at 0. Certainly, I could do the same thing, right? the stuff we just did with the last two functions. I could make a table and use Taylor's formula. Is there a smarter way to do this? A way that is less work?
Use the sin x power series.
Yeah. So we know that the derivative, that cos x is the derivative of sin x, and that sin x is sigma n from 0 to infinity, -1 to the n over 2n plus 1 factorial times x to the 2n plus 1. So rather than cooking up the power series for cosine totally from scratch, why not differentiate the power series for sine? Since cosine is the derivative of sine, if you differentiate the power series for sine, you will get the power series for cosine. And when I do this, I'll have -1 to the n over 2n plus 1 factorial. Remember, we differentiate with respect to x, so the n stuff is all constant. The derivative of x to the 2n plus 1 is 2n plus 1 times x to the 2n. It's a power rule derivative. There is something else that we need to be careful about when we differentiate power series. What is that? You notice I left some stuff off here.
We gain a term.
Something like that can happen. So when we differentiate a power series, it's possible that the starting index bumps by 1, right? This could go from n equals 0 to n equals 1 here. And the question is, does it? So recall, if the original power series has a constant term, then we bump up the starting index by 1. Well, does the power series for sine x have a constant term? The series that we're differentiating here. Does this series have a constant term? What is the very first term of the series for sine x?
X.
Right. Very first term of the series for sine x is 1 over 1 factorial times x. Is this a constant term?
Nope.
No, it's not. So does my starting index jump, or does it stay 0?
Stays at 0.
Very good, it stays 0. Right? We only bump that starting index if the original series has a constant term. If the original series does not have a constant term, then you don't do anything to the starting index because none of the terms disappear. Right? You can think about differentiating it from here. If you differentiate this thing, do any of the terms go to 0? Well, the derivative of x is 1. The derivative of x cubed is 3x squared. The derivative of x to the 5 is 5x to the 4. No, none of these differentiate to 0. If there was like a 2 or a 1 or a 7 as the very first term. If there was a term that didn't have an x, then that term would go to 0. But there is no such term. So this is your power series for cosine. But nobody would leave it this way. I've got a 2n plus 1 up here and a 2n plus 1 factorial down here. So that's 2n plus 1 over 2n plus 1 factorial, which is 2n plus 1 divided by 2n plus 1 times 2n, times 2n minus 1, all the way down to, sorry guys, give me just one. 2n minus 1, all the way down to 3 times 2 times 1. And we can cancel the 2n plus 1s. And we get 1 over 2n times 2n minus 1, all the way down to 3 times 2 times 1. What is this? The downstairs here is the factorial of what?
2n.
2n.
2n, just 2n, very good. And it's like parentheses 2n, all factorial, right? It's 2n times the thing 1 smaller than 2n. It's the product of all the positive integers less than or equal to 2n. So here's your power series for cosine. This is the way everybody writes it. It's sigma n from 0 to infinity, negative 1 to the n over 2n factorial times x to the 2n. Plus x is sigma n from 0 to infinity, negative 1 to the n over 2n factorial x to the 2n. And the IOC here, like the others so far today, all real numbers. Those factorials downstairs really help these series to converge. So I want to summarize what we have so far because I've given you kind of 3 new ultra important power series. Any of you going into any flavor of engineering or hard science, chemistry, biology, physics, fucking whatever, mathematics especially, anything like that. These 3 power series are the most important things in your life from now on. I'm going to write these in terms of the variable u so that we can plug into them the way we were doing at the end of class last time. E to the u can always be written as sigma n from 0 to infinity, u to the n over n factorial. Sine of u can always be written as sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 factorial times u to 2n plus 1. And cosine of u can always be written as sigma n from 0 to infinity, negative 1 to the n over 2n factorial times u to the 2n. These may be the 3 most important facts in the world. And I'm not just saying that. These 3, together with the 2 from last week, the inverse tangent natural log, and 1/1 minus u series. Those are the 5 that I require you to remember, like on the test. So yes, you absolutely should memorize these. Together with the other ones, we had 1/1 minus u is sigma n from 0 to infinity, u to the n. Inverse tangent of u is sigma n from 0, excuse me, 0 to infinity, negative 1 to the n over 2n plus 1 times u to the 2n plus 1. And the natural log of 1 plus u is sigma n from 0 to infinity, negative 1 to the n over n plus 1, u to the n plus 1. These 6 series, before I wasn't thinking of the geometric one, these 6 power series, I fully expect you to remember exactly. These are not ending points for us. These are starting points. So when I ask you to find a power series for e to the negative x squared, you're going to write this motherfucker down, and then you're going to plug in negative x squared for u and simplify. If I ask you to find a power series for the natural log of 1 plus x cubed, you're going to write this thing down and then plug in x cubed for u. If I ask you to find a series for sine x over x, you're going to take this thing, plug in x for u, and then divide the whole thing by x. Right? These are the 6 most important power series in all the land. The 3 on the left are really Mac Daddy. And if we have some time at the end of the term, I will show you how these 3 are connected. You may have noticed that the sine series and the cosine series, if you put them together, are basically this thing. Right? This is like all the odd parts. This is like all the even parts. The only fuckery is the negative 1 to the n, right? So this is like the alternating version of the odd part of e to the u. This is like the alternating version of the even part of e to the u. I'm wearing the wrong shirt for today, but maybe you have seen this sitting around somewhere. E to the I pi plus 1 equals 0. Or maybe you have seen this sitting around somewhere. E to the ix equals cos x plus I sine of x. These statements come precisely from this guy and his connection to these 2. If you plug in I times x for u here, and then split that series up into its even and odd parts, the even parts are cosine, and the odd parts are I times sine. Electrical engineers in particular pay attention, because that identity is the bread and butter of all modern electrical engineering. Yeah, I think there is a strong argument that this is one of the most beautiful statements in all of mathematics. And it's utterly counterintuitive, because there's no intuitive idea what it means to take e and raise it to the I times x. You can't talk about that as repeated multiplication, right? Like e squared is e times e, it's e times itself twice. But e to the I times something, all bets are off, right? And indeed, the correct way to interpret it is through power series. This should be taken as the definition of the exponential function. This is not some consequence. This is not some random formula. This should be the definition of e to the x. But that's enough of me, Ram. All right, so what do we do with this? There's a few things that I'm expecting you to come away from this section with. One of them is the procedure I just described, where you're going to use these as starting points to write down other series by plugging stuff in for you. The other thing I expect you to do is to apply Taylor's formula to other functions besides these, because I mean, we've already done these, right? So let me do one example here that is slightly trickier. Let me pull up your textbook. Maybe We are doing pretty good on time. I might be able to squeeze in a second example. All right, so here's them deriving that formula. E to the x, of course. Don't worry about all this. That's the estimation theorem. I'm not going to beat you up about it. Sin x, cos x, and something at pi over 3. Yeah, the binomial thing is the next thing. I don't want to scare you. So here are these all important series. This binomial series here, I'm not going to require you to remember this. This is not on my list of shit you must remember. Because interpreting binomial coefficients is tricky, to say the least. I'm also not going to make you multiply and divide power series. Good rule of thumb, if you ever find yourself dividing two power series, you done fucked up. But I do want to get us some practice finding Maclaurin series. Yeah. And none of these are really good. That's such a bummer. Sometimes I hate this textbook. All right, we're going to cook up our own. There are plenty of good problems in there, and I will be giving you lots of practice with problems like that. But as far as raw practice with the formula, with the theorem, your book would take this to be a special case of Newton's binomial theorem. I don't think anybody here has enough practice with the regular binomial theorem to start that. No offense, not your fault. Pre-calc here at Santa Fe is kind of fucked up. Let's find the Taylor series and power series for f of x equals the square root of 1 plus x centered a equals 0. Some terminology you're going to run into, by the way. A power series whose center is 0 are called Maclaurin series, M-A-C-L-A-U-R-I-N, Maclaurin. They were discovered first by a different guy. His name was Maclaurin, so we call them Maclaurin series. Fucking same exact thing, just with a equal to 0 instead of like 2 or pi or something. So Maclaurin series and Taylor series, same thing. Maclaurin series just means the center is 0. All right. This guy is not e to the x sine x cos x 1 over 1 minus x natural log of 1 plus x or tangent arctangent of 1 plus x, nor is it any of their derivatives. We have no hope of using the geometric series trick or plugging into one of our other series to get a series for this. So the only path, this is a last resort, the only path here is Taylor's theorem. I'm going to give myself lots of space for the 2 derivative columns because I know that derivatives of this thing are going to get a little gnarly. Remember when I said that those weird factorial-like products show up in power series? Blam. Here's where it's going to happen. So put on your big boy pants. When n is 0, if I differentiate 0 times, this function is, I'll write it as 1 plus x to the 1/2. Not scary at all. Let's plug in 0 for x. I get 1 plus 0 to the 1/2. That's 1. So the constant term, C0, is 1 over 0 factorial, and I'll leave it like that. If I differentiate once, then I get 1/2 times 1 plus x to the negative 1/2. Plugging in 0 for x, I get 1/2 times 1 plus 0 to the negative 1/2. 1 plus 0 to the negative 1/2 is 1, so this is just 1/2. Which means that C1 is 1/2 divided by 1 factorial. I'll leave it like that. If I differentiate again, I get 1/2 times negative 1/2 times 1 plus x to the negative 3/2. And plugging in 0 for x, this 1 plus 0 to the negative 3/2 is just going to be 1. I'm going to write this just as 1/2 times negative 1/2. So C2 is 1/2 times negative 1/2 divided by 2 factorial. This guy is negative. If I differentiate a third time, I will have 1/2 times negative 1/2 times negative 3/2 times 1 plus x to the negative 5/2. Plugging in 0 for x, this piece goes away. It just becomes 1. So I have 1/2 times negative 1/2 times negative 3/2. Which means that C3 is 1/2 times negative 1/2 times negative 3/2 all over 3 factorial. I think we're going to need a few more rows before we start to see the pattern. When n is 4, if I differentiate a fourth time, I get 1/2 times negative 1/2 times negative 3/2 times negative 5/2 times 1 plus x to the negative 7/2. And again, evaluating this at 0, this whole piece goes away, and I just get the product here. 1/2, negative 1/2, negative 3/2, negative 5/2. Which means C4 is that product divided by 4 factorial. 1/2, negative 5/2 over 4 factorial. I think I will do just one more for now. When n is 5. Differentiating this apparatus again, all these constants come along. I'm really just differentiating this piece. You get 1/2, negative 1/2, negative 3/2, negative 5/2. The negative 7/2 comes down. And what's left is 1 plus x to the negative 7/2 minus 1 is negative 9/2. And when you evaluate at 0, you just get the product from the start, which is that 1/2, negative 1/2, negative 3/2, negative 5/2, negative 7/2. So C5 is 1/2, negative 1/2, negative 3/2, negative 5/2, negative 7/2, all divided by 5 factorial. Okay, I'm going to stop with the table here. You see what I mean when I say this column can get a little nasty, all right? Derivatives, successive derivatives of functions, 2, 3, 4, 5 derivatives can get pretty messy, yeah? I imagine, God forbid, we had like a chain rule or product rule thing that we had to differentiate 4 or 5 times, right? It can get quite ugly. What we want to do is find a formula for these CNs. So now that I have, several columns or several rows of this table, I want to look for a pattern over here. And here's my observation. this guy can be written as 1 over 2 to the 1 times 1 factorial, right? Bring the 1/2, that 2 downstairs. This guy, I've got a 1/2 times negative 1/2 upstairs. So that's going to be negative. The 2's from the fractions, 1/2 and negative 1/2, can come downstairs as 2 squared. And then I have 2 factorial. This next guy, I've got 1, 2, 3 copies of 2 that will all move downstairs as 2 cubed. I've got a 3 factorial from the formula. Upstairs, this is a positive times negative, which is positive. And I've got a 1 times 1 times 3. So I'll just write that as positive 1 times positive 3. This next guy, same sort of thing. I've got a power of 2 downstairs. I've got 1, 2, 3, 4 copies of 2. So it's 2 to the 4. 4 factorial. We're seeing the pattern of the denominator now, I hope. Numerator is a little trickier. I've got positive times negative times negative times negative. It's 3 negatives, so this is negative. And then I've got 1 times 1 times 3 times 5, which is 1 times 3 times 5. So what we're seeing develop upstairs is one of those weird factorial-like products. An odd double factorial. C5, last guy. I've got how many copies of 2? 1, 2, 3, 4, 5. So it's 2 to the 5, and then 5 factorial. I've got how many negatives? 1, 2, 3, 4. So this one will be positive. And then I've got 1 times 3 times 5 times 7. And this is looking familiar, hopefully, a little bit. If you had to write down a formula for Cn based on this pattern, what do you notice? Okay, well, positive, negative, positive, negative, positive. Let's see, the C2 term is negative, the C3 term is positive, the C4 term is negative, the C5 term is positive, so I'll have a negative 1 to the n plus 1. And then I have a fraction where the downstairs is always 2 to the n times n factorial, right? 2 to the 1, 1 factorial, 2 to the 2, 2 factorial, 2 to the 3, 3 factorial, 2 to the 4, 4 factorial, 2 to the 5, 5 factorial, Cn, 2 to the n, n factorial. The product upstairs is the fun one. C3 has 1 times 3, the product of the first 2 odd numbers. C4 has 1 times 3 times 5, the product of the first 3 odd numbers. C5 has 1 times 3 times 5 times 7, the product of the first 4 odd numbers. So in general, Cn will have 1 times 3 times 5 out to 2. We want the product of the first n minus 1 odd numbers. So we know that the nth odd number is like 2n plus 1 or 2n minus 1. Let's see, if you plug 5 into 2n minus 1, what do you get? That's 10 minus 1 is 9, not 7. So this is going to be the n minus first odd number, which is 2n minus 3. Right? If you plug 5 in here, you get 2 times 5, which is 10, minus 3, which is 7, and that product does stop at 7. If you plug 4 in here, you get 2 times 4 minus 3, which is 8 minus 3 is 5, and that product does stop at 5. This formula works great, but not for all values of n. If you try to plug in 0 to this formula, C0 here would be negative 1 to the 1, which would be negative, oops, 1 times 3 times 5 all the way out to -3, double oops, I don't know what the hell is even that. And then 2 to the 0 times 0 factorial. The denominator looks okay. But this definitely does not work when n is 0. It also doesn't work when n is 1, I think. Maybe it does. Let's see. Nope. So if you plug in n equals 1, this would be -1 squared, which is positive. Okay. 2 to the 1 times 1 factorial. Okay. But 1 times 3 times 5 all the way up to 2 times 1 minus 3 would be the product of all the n odd numbers out to -1. So this formula works great for n greater than or equal to 2, but not for n equals 0 or n equals 1. This is the correct formula, right? It's just that this formula doesn't make sense when n is 0 or 1. And there's really nothing we can do to make it make sense for 0 or 1. It's not like I've written this down in some unpleasant form. It's just that this product and the numerators here are 2n minus 3 double factorial. This is the thing. It's just that you can't define this when n is 0 or 1. So what do we do? Well, I can say that my function is definitely, by Taylor's formula, sigma n from 0 to infinity, Cn x to the n. And for n greater than or equal to 2, I have a nice formula for Cn. But for n equal to 0 or 1, that formula doesn't work. So what we do is we pull out those first two terms. And I write this as C0, that's the n equals 0 term, plus C1x, that's the n equals 1 term, plus sigma n from 2 to infinity, Cn x to the n. In this series, n is bigger than or equal to 2. And these two guys I've calculated explicitly already. This is just 1, and this is just 1/2. So the power series here is 1 plus 1/2 x plus sigma n from 2 to infinity, -1 to the n plus 1. 1 times 3 times 5 out to 2n minus 3. Divided by
Wait, how is 1 over 0 factorial 1?
0 factorial is 1. If you go back to the first day we introduced the factorial, I gave you a couple arguments to justify the definition that 0 factorial is 1. But some people would just say by definition, the definition of 0 factorial is 1. We said the factorial, the first time we looked at it, we said the factorial is a recursive sequence whose first terms are 1, and then whose successive terms are found by multiplying all the previous terms. So it is true that 0 factorial is 1. So 1 over 0 factorial is 1 over 1, which is 1. But this would be our answer here. Now, when I taught this class at UF, I would regularly put a series like this on the exam. I felt it was fair at the time, and I still feel like it's reasonable. But also UF semester is about 1 week longer than our semester. Bummer. So they get to spend a little bit more time farting around with this stuff. I only say that so that you're aware of the standards that exist at other places. I'll tell you what I would do similar to this on a test in your class. Rather than expecting you to come up with the full sigma notation deal here, I could, on your test, ask you for like the first 5 terms of this power series. All right, so you would cook up the table and just write out the first 5 terms explicitly. In your homework, I certainly could ask you to come up with the full banana here, but I won't do that to you on a test. I do want you to practice it though. This is the reason why we spent some time messing around with these weird factorial-like products earlier, to sort of prepare you for this material. Next time, I'm going to show you a bunch of problems we can solve by plugging into those power series that we cooked up at the start of class, those 6 power series from the beginning. And we'll integrate and differentiate them to get other stuff, all sorts of fun things like that. I am going to go ahead and post a new homework set for you guys today. And the good news is this is the last homework set where you're going to have to do anything with series. So hooray for that. I know we'll all take a deep breath once that is done. And after that, we're going to move on to the last few topics for the class, which are like parametric equations, polar coordinates, and doing things like arc length and surface area in those settings. So I'm going to end the class here for today. Please do look for that new homework in WebAssign. Please do work these problems carefully. If you haven't finished any of the other series homework, you really want to finish that before you get into this. If you have any questions for me, I do have an office hour today from 1 to 2, or you can come by, or you can send me an email, Canvas message, you know the deal at this point. Working on your tests, I promise they'll be done soon, just haven't had the time to do everything yet, but I am in the process of grading those. So that's it from me. Hope you guys have a good rest of your day. Try to keep up with this stuff. If you're feeling lost or in trouble, please come ask for help. All right.